Hello and welcome to CodeChef. Today we are starting an exciting journey into one of the most fundamental topics in computer science, sorting. If you've ever organized your bookshelf, arranged files alphabetically, or seen a leaderboard in a game, you've encountered sorting in action. Sorting is absolutely everywhere in computing, from search engine ranking results to social media organizing posts by time. Understanding sorting algorithms is crucial for any programmer, and today we'll discuss why. Before we start, make sure you have the CodeChef compiler ready to practice. The link is in the description below. Let's learn why sorting is so important and solve our first sorting problem together. Let's get started. Outro.
Binary search. So what exactly is binary search? Binary search is a searching algorithm that works on sorted data. Instead of checking every element like linear search, it uses a brilliant strategy: divide and conquer. Here's a real-life example everyone can relate to. Imagine you're looking for the word electronic in a dictionary. Would you start from page 1 and check every word? Of course not. You'd do something smarter. You'd open to the middle. You'd land around letter M. You'd compare electronic starts with E, which comes before M. You'd eliminate the half. So you know the word must be in the first half, so you ignore everything after the M. You repeat. Now you look at the middle with the first half around F. You compare again. E comes before F, so focus on the first half again. Keep going, keep dividing until you find electronic. Each step eliminates half of the remaining pages. This is binary search. The key requirement is the data must be sorted. Binary search won't work on unsorted arrays. So today we'll learn about how binary search works step by step, the search space concept, implementation in code, and time complexity analysis. Now let's dive in. The search space concept. Before we jump into the algorithm, let's understand the concept of search space. Search space is a range of values where our answer could possibly exist. We represent this range using 2 pointers. Left pointer marks the beginning of search space. Right pointer marks the end of search space. Initially, the search space is entire array. Here's a visual representation. So this is our array, and the leftmost marks the beginning of the search space, which is the left pointer. The rightmost, which is the right pointer, marks the end of the search space. Binary search strategy. Now look at the middle element of the current search space. Compare it with the target, and based on the comparison, eliminate half of the search space. Repeat until we find the target or run out of the space. This should be our strategy. A key insight is, because the array is sorted, if the middle element is too large, we know the target must be in the left half. If the middle element is too small, the target must be in the right half. We can safely ignore the other half. Calculating the middle. We can calculate the middle by middle is equal to left plus right divided by 2. This gives us the index of the middle element between left and right. Binary search algorithm. Now let's break down the complete binary search algorithm step by step. Suppose our problem is search for element k in a sorted array A of size n. Now first we initialize search space. At the left we have 0, which is the start of the array, and the right we have n-1, which is the end of the array. Now loop while search space exists, while left is smaller than or equal to the right. Then we calculate the middle. Middle is equal to left plus right divided by 2. Okay, we compare A, the middle element of A, with K. If the middle element is equal to K, we found it. We return the index middle. And if the middle element is smaller than K, then K must be in the right half. And we update it as left is equal to middle plus 1. We can ignore everything from left to middle. Now suppose if A is greater than K, then K must be in the left half. We update right is equal to middle minus 1, and we can ignore everything from middle to the right. If the loop ends and left is greater than the right, then K is not present in the array. Return -1 or not found. Let's search for K is equal to 7 in array, which is shown here. In iteration 1, we have found array, this is our leftmost element, this is our middle element, and this is our rightmost element. Now, middle is equal to 0 plus 8 divided by 2. That's how we found the middle, okay? This is 0 and this is our 8th element. So we add 0 plus 8 and we divide it by 2 to get 4, which is our middle element. So 0, 1, 2, 3, 4. So 10 is our middle element. Now our middle is equal to 10. Now 10 is greater than 7. So we search the left half and we update right is equal to middle minus 1, which is equal to 3. Now in iteration 2, we will calculate middle again, which is 0 plus 3 divided by 2. We previously update our right as to 3. So now we divide it by 2 and we get our middle as 1. Our new middle is equal to 3 and 3 is greater than 7. So search right half. So we update left is equal to middle plus 1, which is 2. Now in our third iteration, we know our left is 2, our right is 3. Now we calculate our middle again, which is 2 plus 3 divided by 2, which gives us 2. So now our new middle is 6, which is our second element. And here we know 6 is smaller than 7, so we search right half and we update left is equal to middle plus 1, which is 3. In iteration 4, we know right is our third element. So now we calculate our middle, which is 3 plus 3 divided by 2, which is 3. And our third element is 7. 7 is equal to 7. So we have found it and we return index 3. Time complexity analysis. Now let's understand why binary search is so efficient by analyzing its time complexity. Our best case is big O of 1. Our best case is when the middle element itself is the target on the first step. This happens in constant time. Our worst case is big O of log n, which is where binary search really shines. Why log n is at each step we divide the search space by 2. We start at n element. After step 1, it is n by 2 elements. After step 2, n by 4. After step 3, n by 8. And so on and so forth. And after step k, it becomes n divided by 2 raised to k elements. We stop when we have one element left. So n divided by 2 raised to k is 1. So if n divided by 2 raised to k is 1, n is equal to 2 raised to k and k is equal to log to the base 2 n. So the maximum number of steps is log to the base 2 into n. So this is a comparison of how many elements binary search can search through in how many comparisons. So a mind-blowing fact is that binary search can search through 1 billion elements in just 30 comparisons.
Amazing job today. You've learned why sorting is fundamental to computer science and understood key properties that differentiate sorting algorithms. Now head over to the CodeChef compiler and practice. Try sorting different numbers of elements, experiment with the 3-number sort, and think about how you might extend this to more numbers. Keep coding, keep learning, and I'll see you in the next video.